So little Jordan rides his toboggan down a 120-meter long sledding hill that is inclined to 22 degrees. Fully analyze the situation. Um, so with that said, we were able to calculate the acceleration from what we did previously with minus 10 meters per second squared times the sine of the angle of the plane or the hill, and the angle here was 22 degrees, so we just put that in. Now, what other information can we add to our chart? Well, we assume that he's starting here at 0 meters per second, so we'll add that. It's 120 meters long. It's going down, so we minus 120 meters. And now we can solve for the rest of the information using some equations. Well, this is one that comes up a lot. The VF squared equals VI squared plus 2A delta S. VI is 0. A is minus 3.75 meters per second squared. Delta S is minus 120 meters. So VF squared equals 900 meters squared over second squared. We take the square root of that, and we get 30. Now, in this case, it would be minus 30 since it was going down, because both minus 30 and plus 30 satisfy that situation. The average velocity would be minus 15 meters per second. VF minus VI would be minus 30 meters per second. And we could solve for delta T from A equals delta V over delta T. Bring the delta T up. Divide by A. Delta T is delta V over A, which was minus 30 meters per second over minus 3.75 meters per second squared, which is 8 seconds. Put that in there. We can see that it's seconds by the fact here we have meters over seconds divided by meters per second squared, which is the same thing as meters over seconds times seconds squared over meters. Those cancel. One of the seconds cancels, and we have seconds. Just to look at the unit with a dimensional analysis. In the next problem, we have a matchbox car sliding down a 2.5 meter long ramp in 6.5 seconds. We want to know the inclination of the ramp. So we're wondering what theta is for this ramp. And the matchbox car goes down the ramp. And it goes down 2.5 meters. Of course, our delta S here is going to be minus 2.5 meters. Assume VI is 0. And the time, 6.5 seconds. Well, the first thing, if we get A, we can work backwards from A equals G sine theta. We'll use our really good chart to get A. We know what G is, and then we can solve for theta. So, chart in now, add some information. In this case, we have 0 meters per second. We have 6.5 seconds. We have minus 2.5 meters. And we could see here we could solve for some information. We have the equation VF equals VI plus A, but that's not going to work because I don't have A. But A delta T is what I was thinking. But we can't do that yet. But we could do the V bar is delta S over delta T. Minus 2.5 meters over 6.5 seconds. That gives us minus 3.8, or 0.38, sorry, minus 0.38 meters per second. So that will go in here. So now once we have that, we can then get VF because V bar is VI plus VF over 2. If we know that that's minus 0.38 meters per second and VI is 0, we can multiply the 2 up, and VF will be minus 0.77 meters per second. Delta V, therefore, is minus 0.77 meters per second. Now we can get our A. Delta V over delta T, minus 0.77 meters per second over 6.5 seconds. Minus 0.12 meters per second squared. Of course, this is assuming frictionless conditions. So okay, so now we have to go back and get what theta is by plugging this in. So we have this A equals G sine theta. Well, A was minus 0.12, and G is minus 10. Like that. And then we could solve that by dividing 0.12 divided by 10. Oh, imagine that. 0.012 equals sine theta. And then to solve for the angle, we do the sine inverse.